Welcome to the Daily History Chronicle. Each day, we travel back to discover a pivotal moment that changed the world. These aren't just dates and facts. They're stories of courage, conflict, innovation, and consequence that still echo through our lives today. Are you ready to explore? Let's see what happened on this day in history.
Good morning and welcome to today's episode. I'm Richard Backus, publisher of University Teaching Edition, and each day I invite you to join me as we reflect on a significant moment from our shared past. Today is November 27th, and we're looking back 324 years to November 27th, 1701. On that day, in Uppsala, Sweden, a boy was born who would give the world something we use every single day, often without thinking about it, a standardized way to measure temperature. Anders Celsius would become an accomplished astronomer and mathematician, but his lasting contribution to humanity was a temperature scale, so intuitive and practical that it's now used by virtually every country on Earth, except, stubbornly, the United States. The Celsius scale seems simple. Water freezes at 0 degrees and boils at 100 degrees. Easy to remember, logical, based on a substance everyone knows. But creating this scale required insight into making science communicable, establishing standards that everyone could use, and basing measurements on reproducible reference points rather than arbitrary choices. The story of Anders Celsius and his temperature scale is really about something larger, the challenge of creating shared systems that allow people to communicate precisely across languages, cultures, and continents. It's about why standardization matters, why some countries resist international standards, and how the measurements we use shape the way we think. And it reminds us that even something as seemingly objective as temperature is, at its core, a human construction, useful precisely because we agreed to use it. Anders Celsius was born into Swedish scientific aristocracy. His father was a professor of astronomy at Uppsala University. His grandfather had been a mathematician and astronomer. Young Anders seemed destined for science from birth. He followed the family path, studying at Uppsala and eventually becoming professor of astronomy there in 1730. His early work focused on observing the aurora borealis, the northern lights that illuminated Swedish winter skies. He was fascinated by the possibility that magnetism, a prescient idea, might influence these lights, though he lacked the tools to prove it. Celsius participated in an expedition to measure the shape of the Earth. Newton's physics predicted that Earth should bulge at the equator and be flattened at the poles due to rotation. To test this, expeditions measured the length of a degree of latitude at different locations. Celsius joined the expedition to Lapland in 1736, enduring brutal cold, to take measurements that confirmed Newton's prediction. The Earth was indeed an oblate spheroid, not a perfect sphere. This expedition was crucial to Celsius's later work on temperature. In the Arctic cold, he saw how existing temperature scales failed. Different thermometers gave different readings. There was no standard reference point that everyone agreed on. Scientists couldn't compare their measurements because they weren't using the same scale. This was more than inconvenient. It made rigorous science nearly impossible. The problem was fundamental. Without standardized measurements, science couldn't progress. You couldn't verify someone else's experiment if you couldn't reproduce their conditions. You couldn't compare observations from different locations. You couldn't build on previous work. Science requires precision, and precision requires standards. Before Celsius, measuring temperature was chaos. Several different scales existed. Daniel Fahrenheit developed his scale in the 1720s, choosing the temperature of a mixture of ice, water, and salt as his 0 point, the coldest temperature he could reliably create, and using human body temperature as 96 degrees, later adjusted to 98.6. These choices were arbitrary but worked for Fahrenheit's purposes. René Reaumur developed another scale in 1730, using the freezing point of water as 0 and its boiling point as 80 degrees. Why 80? Because that's how many degrees his alcohol thermometer expanded between those points using the particular alcohol mixture he chose. Isaac Newton had proposed yet another scale. The old Romer scale was different still. Each scientist used reference points that made sense to them but seemed arbitrary to everyone else. And worse, different thermometers using the same scale often gave different readings because the instruments themselves weren't standardized. This wasn't just academic frustration. Doctors couldn't compare patients' fevers. Meteorologists couldn't share weather data. Scientists couldn't verify each other's experiments. The lack of a universal temperature standard was holding back progress. Celsius recognized that any useful temperature scale needed certain characteristics. It should be based on phenomena everyone could observe and reproduce, not the temperature of a specific person's armpit or a particular mixture of chemicals. It should use simple, memorable numbers. Ideally, it should relate to something fundamental that people encounter in daily life. In 1742, Celsius proposed his scale based on the two most obvious reference points, the freezing point of water and its boiling point. Here's where it gets interesting. Celsius's original scale was inverted from what we use today. He set the boiling point of water at 0 degrees and the freezing point at 100 degrees. Why? Celsius was thinking like an astronomer, not a thermometer user. To him, it made sense to avoid negative numbers. In Swedish winter, temperatures drop well below the water's freezing point. If freezing was 100, then winter cold would still be positive numbers. This seems backwards to us now, but it reveals something important. Measurement scales are arbitrary. There's no correct direction for temperature. We could count up as easily as down, as long as everyone agrees. Within a few years of Celsius's death, in 1744, he died at only 42 from tuberculosis. The scale was inverted to the form we use today. 0 for freezing, 100 for boiling. Who made this change isn't entirely clear. Possibly Carl Linnaeus, the famous botanist and Celsius's colleague, or possibly instrument maker Daniel Ekstrom. But the change was clearly practical. It's more intuitive to have temperature rise as things get hotter. The scale was sometimes called centigrade, from Latin for 100 steps, rather than Celsius, though in 1948 it was officially renamed the Celsius scale to honor its creator. The name centigrade is confusing because it was also used for a unit of angle measurement. The Celsius scale triumphed over its competitors for several good reasons. First, the reference points were universal and reproducible. Anyone, anywhere, could observe water freezing and boiling, adjusting for altitude and air pressure, which was understood. You didn't need special equipment or specific substances. Water was everywhere, and its phase transitions were clear. Second, the 100-degree span was memorable and convenient. Dividing the interval into 100 equal parts made calculations easy, especially as the metric system with its base 10 structure became standard. Want to know the midpoint between freezing and boiling? 50 degrees. Simple. Third, it aligned with the emerging metric system. The metric system, developed in France in the 1790s, was based on powers of 10 and used reproducible natural phenomena as references, like the meter being defined as 1/10 millionth of the distance from equator to North Pole. Celsius's scale fit this philosophy perfectly. Fourth, it made sense for daily life. Most human activity happens between water's freezing and boiling points. The Celsius scale puts typical temperatures in a convenient range. Winter cold is negative, summer heat is positive, and the range most people experience spans roughly -20 to +40 degrees, numbers that are easy to conceptualize. By the late 18th and early 19th centuries, Celsius was becoming the standard in scientific work. By the 20th century, most countries had adopted it for everyday use as well. Today, it's the official temperature scale in every country except the United States, a few Caribbean nations, and Palau. That's over 95% of the world's population using the Celsius system. Which brings us to the excellent temperature puzzle. Why does the United States still use Fahrenheit? The United States adopted Fahrenheit early, when it was the dominant scale in British territories. By the time Celsius became standard elsewhere, Americans were thoroughly accustomed to Fahrenheit. They knew that 32 degrees was freezing, that 70s were comfortable, that 100 was very hot, that body temperature was 98.6. These numbers had meaning, and changing them seemed unnecessary. There have been attempts to switch. In the 1970s, the United States officially adopted the metric system and began a metrication program that included changing to Celsius. Road signs were erected with kilometer markers. Weather forecasts gave both Fahrenheit and Celsius. Schools taught metric measurements. It looked like change was coming. But it didn't take. Americans resisted. The dual system confused people rather than educating them. Politicians responded to constituent complaints by defunding metrication efforts. By the 1980s, the push had essentially failed. Metric measurements remained standard in science, medicine, and certain industries, but daily life stayed imperial: miles, pounds, and Fahrenheit. The reasons for American resistance are complex. Part is simple inertia. Changing millions of thermostats, ovens, weather reports, and people's mental frameworks is expensive and disruptive. Part is cultural identity. Metric is seen as foreign, imposed by international bodies, a threat to American distinctiveness. Part is practical. Fahrenheit's more minor degrees give more precision without decimals for typical temperatures. But the cost of this holdout is real. American children must learn two systems. Scientists constantly convert. International communication is complicated. Travel requires mental math. And America looks stubborn and provincial to a world that long ago standardized on Celsius. The Celsius story illustrates why standardization matters far beyond temperature measurement. Standards enable communication. When scientists worldwide use Celsius, they can share data directly without conversion errors. When engineers use metric measurements, they can collaborate across borders seamlessly. Standards reduce friction and enable cooperation. Standards prevent disasters. In 1999, NASA's Mars Climate Orbiter crashed because one team used metric units and another used imperial units, and the error wasn't caught. The spacecraft was destroyed. This $125 million failure occurred because of unit confusion, exactly the kind of problem standards are supposed to prevent. Standards enable trade. ISO standards for shipping containers revolutionized global commerce by allowing any container to fit any ship or truck. Electrical standards allow appliances to work across regions. Without standards, international trade would be vastly more expensive and complicated. Standards shape thinking. The measurements we use influence how we conceptualize problems. Celsius's 0, 100 scale for common temperatures creates an intuitive framework. Metric's base 10 structure makes unit conversion simple. The tools we use to measure reality affect how we understand that reality. But standards also represent power. Who decides the standard? English became the global language partly because of British and American economic dominance. The metric system spread partly because of French cultural influence and partly because European colonial powers imposed it on their colonies. Standards reflect the values and choices of whoever establishes them. The resistance to standards can therefore be political, not just practical. Keeping Fahrenheit is partly about preserving American identity and resisting European influence. Language standardization efforts face resistance from speakers of minority languages who see their culture threatened. Standards can homogenize, erasing local differences and preferences. Today, we face new standardization challenges that echo Celsius's time. How do we measure digital phenomena? What's the standard unit for data? Bytes, gigabytes, and terabytes are quasi-standard, but different systems sometimes use different prefixes, decimal versus binary. How do we measure internet speed, algorithm efficiency, or carbon footprint? We're still negotiating these standards. How do we standardize across cultures? Time zones are standardized, but dates formats aren't month-day-year versus day-month-year versus year-month-day. Currency conversion requires real-time exchange rates. Even simple things like paper sizes differ, A4 versus letter. As the world grows more interconnected, these incompatibilities cause friction. How do we balance standardization with flexibility? Rigid standards can stifle innovation. Too many standards create confusion. The optimal level of standardization isn't obvious. Sometimes competing standards drive innovation until one emerges dominant. Sometimes they just create waste and incompatibility. Climate change has made temperature measurement particularly crucial. Global temperature records require comparing measurements from thousands of stations over centuries using different instruments and techniques. Standardization, knowing that a degree Celsius means the same thing in 1850 and 2025 in Sweden and Singapore, is essential for understanding climate trends. Celsius's simple, reproducible scale makes this possible. Anders Celsius grasped something profound. Measurements aren't just about numbers. They're about communication, about creating shared frameworks that allow people to collaborate and build on each other's work. His temperature scale worked because it was based on phenomena everyone could observe, used numbers people could remember, and created a framework that made sense for common experience. It was scientific but accessible, precise but intuitive. This is the art of good science communication, making complex phenomena measurable and communicable without sacrificing accuracy. Temperature is actually an incredibly complex concept, the average kinetic energy of molecules. But Celsius made it graspable. 0 is freezing, 100 is boiling, and everything in between makes sense. The fact that his scale is now used by billions of people daily, almost none of whom know his name, is the ultimate success. Good standards become invisible. They work so well that we forget they're human creations, that someone had to invent them, that they represent choices that could have been made differently. Fahrenheit, Réaumur, and others created perfectly functional temperature scales. Celsius won not because his was objectively correct. There is no objectively correct temperature scale, but because his was intuitive, reproducible, and aligned with emerging international scientific standards. He understood that usefulness matters more than originality, that adoption matters more than innovation. In a world often divided by language, culture, and politics, shared measurement systems are one of the few universal languages we have. When a scientist in Japan reads a paper by a researcher in Brazil reporting results at 37 degrees Celsius, they know exactly what that means. No translation required, no cultural context needed. When an engineer in Germany designs a component for a factory in India, they use millimeters and Celsius, confident the measurements mean the same thing on both continents. This is Celsius's legacy, not just a temperature scale, but a contribution to the infrastructure of global communication and cooperation. It's easy to take for granted. We check the weather, see 15 degrees or 25 degrees, and barely think about it. But those numbers work because centuries ago, a Swedish astronomer recognized the need for scientific standards and created one elegant enough for the world to adopt. The United States will probably adopt Celsius for everyday use eventually. The pressure of global integration, the inefficiency of maintaining two systems, and generational change will likely overcome inertia. When that happens, whether it's decades or centuries from now, Americans will join the rest of humanity in using the scale Anders Celsius created. Until then, every time you see a temperature on a weather app, a thermometer, an oven display, you're seeing the legacy of a man born 324 years ago today who understood that measurements matter, that standards enable progress, and that sometimes the most important innovations are the ones that help us communicate clearly with each other. Thank you for joining me today on the Daily History Chronicle. As philosopher George Santayana reminds us, those who cannot remember the past are condemned to repeat it. Today we saw how Anders Celsius created a temperature scale so intuitive and practical that it became the global standard, teaching us that measurements are more than numbers. They're frameworks for communication, and that the most successful innovations often aren't the most complex, but the ones people can understand and adopt universally. The next time you check the temperature, remember that someone had to invent that scale, that it represents choices that could have been made differently, and that shared standards, however invisible they become, are essential infrastructure for human cooperation and progress. Until tomorrow, may your day be enriched by the lessons of history.